Thank you so much, but I'm not a doctor just yet. So, aloha and good morning. I'm really delighted to be able to talk to you about my work today. And I do not have anything to declare. So just why are we here? It's all to do with the ACL and the fact that on conventional MRI, it's basically a black. So this is the sequence that I give my surgeons, and along with a lot of other sequences as well. And you can see you've got very little information going on here because we are not actually collecting any real signal back from the ACL. So what I've been asked to do is to try and quantify the health of the ACL. And this is because the orthopedic surgeons now have got new kinds of implants that they need to only implant into healthy patients who have got healthy cruciate ligaments. And how do they decide whether or not they're healthy? So it's a very subjective method that they're using at the minute. It's basically they open the patient's knee, put a hook in and give it a tug. So, and a lot of those patients are failing later on and needing a revision. So the rationale behind my work is actually completely different to what we've presented here. We know that there's something going on in here and there's an awful lot more information to be gained. So interestingly, the ACLs often lie at the magic angle at 55 degrees, and so you get this increase in signal intensity. And so my work is all about trying to exploit the magic angle phenomenon. And we know that the magic angle is 55 degrees. It's all to do with signal and intensity and how it relates to B0. So if I align it with B0, I get a low signal intensity. And if it's at 55 degrees, you get this high signal intensity. So angle sensitive MRI, basically, you need to have multiple orientations to B0 to actually get some real information from it. And I'm quite lucky that some groups have actually done quite a lot of research on this. So this is the group from UCSD who looked at excised goat meniscus at different angles. They scanned in 15 directions, a protocol that took around about 3.5 hours. And they used 3 different planes of 30-degree increments. This is just 2 of the 15 here. And you can see here this bright signal that's coming from the magic angle and the dark signal where it's parallel to B0. They were able from this to generate these beautiful color maps and also get circumferential fiber tractograms, which was quite amazing. The other group, and this was the early work from Leipzig, they used 35 directions, an excised iliotibial band, but they only scanned in 3 planes. However, they were quite successful. So each of these little dashes indicates the orientation of the neck collagen in that particular voxel. But both of these groups basically said that this technique has potential. It's taking too long at the minute to bring it clinically, and also we can't contort our patients into positions inside the closed bore scanners. So that's where my group comes in. So we have been trying to design a scanner where B0 actually moves around the patient. This was the concept drawing. This is the prototype, which is much, much bigger than the concept drawing, but we're still working on this at the moment. So basically, my part of the project was to try and determine how we would go about scanning a patient clinically using this scanner and how many directions are necessary, and to try and get it within a time that patients would tolerate. So all my work's been done using a Siemens 3T Vario, a clinical scanner. And because B0 is fixed, I've had to devise a method where I actually rotate, and there's a little knee in here. So I'm using an animal model. This is a caprine knee. And this is the setup for 9 directions. And basically, I just move to the next red movement, and the arrows are helping me so I know which directions to rotate the sphere in. To work out how many directions I needed, I compared back to the standard Daffy technique. Now, we worked out fairly early on that we were not going to be able to use this with the magic angle scanner because the patient's leg would actually get in the way. So we had to come up with an idea where we actually more equally distributed the rotations that we needed to make, or the directions that we needed, so that we could actually get those in with the rotations that the scanner was able to actually do. So here's the post-processing steps. Effectively, I take 9 different volumes, or 15 and what have you, at the different angles, and then we have to align them back to the initial position. I then combine all of those volumes and look for the biggest variations in the signal intensity to give me this angle-sensitive volume. From there, I segment out. So what we've made, this assumption is that voxels that show a big change in signal intensity are demonstrating the magic angle effect. And so we just extract those because we've got so many there's far too many to actually, it was taking about 5 days to process this data otherwise. So we really needed to reduce the times. From here, I've worked with a team to improve just slightly the DAFI algorithm to compute the collagen orientation. And because my surgeons couldn't cope without the lines being joined up, we've worked for a different visualization using a open source software called ParaView. So this is just steps 2 and 3, a little bit more detailed. Each of these black squares indicates a voxel that contains a collagen-containing voxel. This is the 2-dimensional, so it's a bit complicated here because basically I've got a number of different slices that contain the ACL, and they're colored up to help us work out the orientation vector of the net collagen direction. And then we've got here the 3D representation. And again, it's quite difficult to actually pick out what's going on. You can see a number of things. But when we go to this, I think you can quite convincingly see that we've got 2 fiber bundles. You have the anterior medial here, which is red, and the posterior lateral that's actually behind it. So how many directions do we actually need? To do this, I took a segmented voxel through the center of the patella tendon of about 100 voxels and then compared it along this line. The timings are here for each of the experiments, and you can see here we've actually brought the time down quite considerably, so it's getting into the rooms of probably a research protocol. If you're good at playing spot the difference, you'll have already noticed that at 9 directions, I've got around about 3 voxels that vary to the standard of the 15. At 7, it went up to about 10 voxels difference, and by 5, it's just, a total fail. You haven't got enough information there to actually compute the collagen orientation at all. And I've also had issues with the alignment. So the more I have, I'm getting edge effect here, so there's very little we can do about that. So we've been trying to quantify this a little bit more. I've developed an anisotropy index. This basically, the comparison here between 9 and 15 is good. The way you view this is from above, so it's like you're looking down on top of the tendon. This part here is represented here, and this part here is represented here. And I can get AI for both of these, but we haven't validated this yet, so this is still work ongoing. But clearly, a permanent magnet that rotates around has a lot less signal to noise. So what I've been doing is adding noise to my data, because we worked out that the greater amount of noise, the more directions were needed. So really for in vivo angle sensitive MRI, we need moving B0 and at least 9 directions. It did actually work with the the signal to noise that we have calculated from the early images from the magic angle scanner, and that's about 3 times faster. So just to conclude now, hopefully these are moving. Yes, they are. So what I can say is that we have been able to show that you can actually use the optimum number of directions is less than previously published. It is all my results are being used now to program the movements of the magic angle scanner. And I think you can see here what I've been able to do in one experiment is to actually look at all kinds of different collagen-rich tendons within the knee. And what we can say for the future is that we're really hopeful that we can actually use this to help improve clinical decisions, because now you can actually see those fibres, and hopefully we'll be able to quantify them and actually give the surgeons a measure of health. So all that remains is for me to thank the team and also the funder, because without them we would not have been able to do this work. Thank you.